Hello, so welcome students to the second lecture of this series on differential equations. Let us briefly recall where we stopped. We were looking at a very innocent looking differential equation dy by dt equal to y squared, and we came up to this point and we found the solution yt equal to c by 1 minus ct. We observe that the solution as time t goes to 1 over c from the left, yt goes off to infinity. The solution blows up in finite time. There's a finite time catastrophe, as it were. This is reason why this happens is because of this y squared term. Instead of y squared, if I put y cube, you will see the same thing happening. In finite amount of time, the solution would shoot off to infinity. There is nothing wrong with the differential equation. The differential equation is defined everywhere. Y squared is a polynomial. Nevertheless, the solution does not live on the entire real line. It lives from minus infinity to 1 upon c. That is, the interval over which the solution exists is usually not the entire real line, but only a part of the real line. It's only a very small part of the real line usually. So this is what I meant in the previous slide when I said that even though the differential equation may be defined everywhere, the interval I, that is I equal to t naught minus a comma t naught plus a, that interval I may not be the whole interval of time. That is, there may be escape to infinity in finite time. The solutions may escape to infinity in finite time. Okay. So let us now look at this phenomenon in a little more detail, maybe in a couple more examples we can see. Before we take that up, there is another small point that I'd like to address. Namely, if you notice, we have been using indefinite integrals. I want to point out, and I've been saying this to all my students, that whenever possible, work with definite integrals. Try to avoid indefinite integrals. There are situations where we cannot do it, or when in some situations it is probably not feasible or it's more clumsy to not to use it. So try to use definite integrals whenever feasible. That's the fundamental mantra I would like to convey. Why? Why should definite integrals be used? Because definite integrals are superior beings. Why are they superior beings? Notice that the integral fx dx from a to b is defined for any continuous function f of x over the interval ab. The symbol has a precise meaning whether or not you are able to compute the indefinite integral, whether or not you are able to find a primitive for f of x. This symbol integral a to b fx dx makes perfect sense. Another advantage is that when you use definite integrals in differential equations, you automatically incorporate the initial conditions. So let us do the same problem again using definite integrals instead of indefinite integrals. So again, let us go back to the differential equation. 1 over y squared dy by dt equals 1. Now we shall integrate both sides with respect to t over a certain interval 0, s. That is, we are looking at a definite integral this time. And what do we get? Integral 0 to s 1 over yt squared into y prime t dt equals integral 0 to s dt. Right hand side, of course, integrates to s. What about the left hand side? Remember, look at the differential equation dy by dt, y prime is y squared, so y prime is positive, right? So y is a strictly monotone increasing function, and therefore I can appeal to the substitution theorem. I put y of t equal to u and I get y prime t dt is du. When t is 0, what was y of 0? C. And when t equal to s, the value of the variable u will be y of s. So the integral using the substitution y of t equal to u transforms into integral c to y of s du by u squared equal to s. Now you can integrate du by u squared and then it will be 1 upon u with a minus sign. Put the initial conditions c and this c and y of s and you simplify and rearrange. You get the same thing. You get y of s equals c divided by 1 minus cs. So I am omitting this little algebra, this problem of integrating du by u squared, putting in the limits, doing the rearrangements and getting your y of s. It's a very trivial exercise and I urge you to carry that out yourself and verify that finally you get y of s equal to c upon 1 minus cs. You have recovered the solution of this differential equation, but this time we have employed systematically definite integrals and not the indefinite integrals as in the previous slides. Okay, and I once again like to remind you that definite integrals are superior beings. The definition makes perfect sense regardless of whether you are able to find the primitive or not, whether you are able to find a function whose derivative is the given function, the antiderivative as it were. Integral of cosine x is sine x plus c because the derivative of sine x is cosine. That is, an antiderivative of cosine is sine. In this case, it is easy to figure out what the antiderivative of cosine is. But in many cases, as you know, determining the antiderivative is not easy. It's tricky. Sometimes it's not possible at all for you to find a function whose derivative is a given function. But when we deal with definite integrals, remember, are defined as areas and they have a very precise and rigorous mathematical meaning. So they are always superior objects. Alright, so now let's go to two exercises. Consider the differential equation dy by dt equals 1 plus y squared. Initial conditions are prescribed, y of 0 equals 1. Does the solution escape to infinity in finite time? What if the right hand side is replaced by 1 plus y to the power 10? So let us pause and think about how to do this question. You see, your initial impulse will be, let us integrate this differential equation. Okay, let's try it. Let's do it. Let's go whole hog and compute the integral and determine the solution and then answer this question whether the solution escapes to infinity in finite amount of time. Alright, so let's see. So your differential equation is dy by dt equals 1 plus y squared. There is absolutely no problem in dividing by 1 plus y squared since it's always positive. Integrate over some interval, say 0 to s. What do you get? When time t equal to 0, we have prescribed the initial condition to be 1. Integral dy divided by 1 plus y squared equal to integral dt from 0 to s, which is s. That will give you tan inverse of y of s minus tan inverse of 1 equals s, or you get y of s equal to tan of s plus pi by 4. So you got the solution. Well, so from this solution, you will say, okay, you will examine this solution. You will examine this solution and then you will figure out when s approaches pi by 4 from the left, the solution y of s goes to plus infinity. This is all very fine, but let's go to the problem. Let's go back to the problem and see what's being asked. What's being asked? You're being asked, does the solution escape to infinity in finite time? You're not asked to determine the solution. And the other problem is that the right hand side, instead of 1 plus y squared, would be 1 plus y to the power 10. Now, suppose you have 1 plus y to the power 10 and you try to solve the differential equation, you will end up having to integrate dy by 1 plus y to the power 10. And that's going to be exceedingly tedious. It's going to be time consuming and tedious, whereas all that is being asked is, does a solution escape to infinity in finite time? Alright, well, so question, how on earth are you going to answer this question without explicitly finding the solution? One can do that, and let's see how to think about that. It's very easy and it shows a very important principle in the theory of differential equations. So, what's given to you? You are given dy by dt equals 1 plus y squared, y of 0 equals 1. Well, you can certainly say dy by dt exceeds y squared. Surely you will agree with me that 1 plus y squared is bigger than y squared. It's strictly bigger, as a matter of fact. So now we can do the same thing. Now y squared is positive, remember. So 1 upon y squared dy by dt is strictly bigger than 1. Now integrate. Now integrate over, say, 0s. What do you get? You get integral when t is 0, when time t is 0, what's the value of y? Value of y is 1. So it will be 1 to y of s du by u squared greater than s. When you integrate 1, you get s over the interval. Well, now you can continue the calculations, and then, so what do? We do this minus 1 upon u from 1 to y of s greater than s. That will give me 1 minus 1 upon y of s bigger than s, or 1 minus s bigger than 1 upon y of s. So this would mean y of s exceeds 1 upon 1 minus s. We immediately see that as s goes to 1 from the left, the right hand side of the displayed inequality in red, goes to infinity. Thus, the solution y of s certainly cannot live beyond s equal to 1. In fact, we have seen that the solution goes to infinity at pi by 4, which is actually less than 1. Now, what have we done? We have done a very simple thing. We have gone from the differential equation to a differential inequality. We simply knock off this 1 and we say dy by dt is bigger than y squared, and the rest of the calculation was very simple. So even if you have 1 plus y to the power 10, we can do the same thing. We can simply knock off the 1 and you can say dy by dt exceeds y to the power 10. We can divide by y to the power 10 and proceed along the same lines. Nothing stops us from doing that. So the point is that it's not necessary to solve the differential equation completely. It's enough to get to replace it by something else. And it's not necessary to solve the differential equation. Without solving the differential equation, we can still draw our conclusions, and that is the most important thing. In the theory of differential equations, one seldom solves the differential equation to completion. One often obtains behavior of the solutions without explicitly carrying out the solution to the end. Without determining the solution explicitly, we try to obtain properties of the solution. That's what the theory of differential equations is all about. Now let me insert an important comment. Note that we have passed from the differential equation dy by dt equal to 1 plus y squared with y of 0 equal to 1 to the differential inequality dy by dt bigger than y squared with y of 0 equal to 1, and then we concluded that y of s is bigger than 1 upon 1 minus s, which means y of s would already have gone to infinity by the time s goes to 1. Note that we are not saying that y of s becomes infinity exactly as s goes to 1. We are saying that y of s goes to infinity either as s goes to 1 or perhaps before that. That is, the time of existence y of s cannot exceed 1, but it can actually be strictly smaller than 1. We saw this. We actually integrated the differential equation, the first display in the slide, dy by dt equal to 1 plus y squared with y of 0 equal to 1. We actually integrated this differential equation. We found that the solution is y of t equal to tan of t plus pi by 4, and we saw that the solution goes to infinity as t tends to pi by 4. So, the solution becomes infinity before time t equal to 1. So, what our differential inequality tells you is that the time of existence cannot be greater than 1, but it can be actually less than 1. Now, the next problem is to answer the same question, but instead of dy by dt equal to 1 plus y squared, I am giving you dy by dt equals 1 upon 1 plus y squared. 1 upon 1 plus y squared. Again, you multiply by 1 plus y squared, integrate both sides with respect to t, use definite integrals, recommended, but you can also use indefinite integrals if you like. That's your choice, but here it's recommended wherever possible to use definite integrals. So you can try the second problem yourself and try to figure out whether the solution escapes to infinity in finite amount of time or does it live forever. Alright, so there are two simple exercises based on separating variables, that is bringing the y squared on the left and integrating with respect to t and so on. Now let us take the third problem. Here we consider the problem cosine x into 1 plus sine y dy by dx equals 1 plus sine x into cosine y. Again, it's a variable separable equation. Remember what dy by dx equal to f of xy. So this factor cosine x into 1 plus sine y, you put it on the right hand side, and what do you get? The right hand side is a function of two variables, f of xy, and it's a product of a function of x times a function of y. So whenever the right hand side, that whenever you have dy by dx equals gx into hy, we refer to the differential equation as a variable separable equation. This is also a variable separable equation. The dy by dx is a product of a function of x alone times a function of y alone. Here, of course, because of the presence of the cosine here and a cosine there, I am going to assume that x and y lie in the open interval minus pi by 2 to pi by 2. We are going to work in the open interval minus pi by 2 to pi by 2. Okay. Alright. The problem continues. Prove that the solution y of x is defined on the entire interval minus pi by 2, and as x approaches pi by 2, the solution y of x approaches pi by 2. Discuss the special case where the initial conditions are specified, y of 0 equals 0. Here for a change, I am giving you an indefinite integral. Just for a change, let's work with indefinite integrals, although they are inferior beings, never mind. They also have a right to live, as it were. So let us separate the variables, as it were. Let us divide by cos y and let us divide by cos x, so that the y variables are all on the left and the x variables are all on the right, and perform an integration. You can integrate 1 upon cos y. 1 upon cos y is secant y. What is the integral of secant y with respect to y? It is log secant y plus tan y. There is no need to put the absolute value because we are in this interval minus pi by 2 to pi by 2 where the thing is positive. Secant y plus tan y. What is that? It is going to be 1 plus sine y upon cos y. Cosine is an even function, it's positive, and 1 plus sine y is also positive. There is no need for an absolute value sign. So that is the integral of 1 upon cos y is log secant plus tan. And then you have got the integral of sine y by cos y. That is integral of tan y dy. And the integral is log secant. So you got sum of two logs. It will be a log of product. So the left hand side will integrate as log of secant squared y plus secant y tan y. And then you see a lot of symmetry here. What you see with y on the left, you see the same thing with x on the right. So when you integrate the same song and dance, it will be log secant squared x plus secant x tan x. So you will get, when you integrate this, you will get a log secant squared y plus secant y tan y. Let me just slow down a little bit by actually inserting a couple of lines. All right. You're getting on the left hand side, you're getting log secant squared y plus secant y tan y equals log secant squared x plus secant x tan x plus a constant of integration c. Exponentiate secant squared y plus secant y tan y equal to e to the power c into secant squared x plus secant x tan x. So here we stop and here we say that this is the solution. Well, you might object, you might say that the solution should be y equal to something. That's not the form in which we got the solution. What form have we got? The solution is described in implicit form. You have studied implicit functions and implicit differentiation in the differential calculus part of your curriculum. You encountered implicit functions, and so here the y is a function of x but described implicitly. This is going to happen in the whenever you solve differential equations of the first order. Usually the solution will present itself in implicit form as it happens here. Alright, so the solution is given in implicit form. So let's go back to the slides. Yeah, you see that secant squared y plus secant y tan y equals e to the power c into secant squared x plus secant x tan x. What does the problem ask you? The problem, look at the problem again. Prove that the solution is defined on the entire interval minus pi by 2 to pi by 2. That's obvious that here the solution is defined on the entire interval. Nothing happens when x on this interval. I mean, as long as you're on the open interval, there doesn't seem to be any kind of trouble in this equation. Well, let's look at what the problem is asking again. As x tends to pi by 2, you have to show that the y of x also goes to pi by 2. Look at what happens on the right hand side. Secant squared x plus secant x tan x. What is that? That is 1 plus sine x upon cosine squared x. Right hand side is 1 plus sine x upon cosine squared x. As x approaches pi by 2, 1 plus sine x approaches 2. The denominator cosine squared x approaches 0. And so this factor secant squared x plus secant x tan x goes to plus infinity. And that second factor is a constant. So compulsorily this secant squared y plus secant y tan y must go to infinity. Incidentally, Notice that the differential equation tells you that dy by dx is always positive. Remember, cos is positive, 1 plus sine is positive on this interval, there is no problem. And so dy by dx is positive. So the solution yx is a monotone increasing function. And as x goes to pi by 2, it is compulsory now that from this equation, we compulsorily see that y of x must also go to pi by 2. Y of x monotone increases to pi by 2. So that answers the question. In the last example, study what happens when x tends to minus pi by 2. So I am leaving it to you to study what happens to this function secant squared x plus secant x tan x. What happens when x goes to minus pi by 2? Well, what is it? It is 1 plus sine x upon cos squared x. As x goes to minus pi by 2, the numerator goes to 0 and so does the denominator. So it is a 0 by 0 form. So you know how to deal with such limits. You have done many such limit problems, and it's an amusing exercise for you to find out what happens to the limit as x goes to minus pi by 2. And so you likewise investigate what would happen to the corresponding yx as x goes to minus pi by 2. So that is something for you to think about. The next question is, if the initial condition is y of 0 equal to 0, right? If y of 0 happens to be 0, that is when x is 0, then y is also 0. So what happens to the last displayed equation that you see here in this slide in red? You put x equal to 0 in this equation that is displayed in red. Then what happens? Y of 0 is 0, remember? So x is 0 and y is 0. The tan x becomes 0 and the tan y becomes 0. The secant x becomes 1 and the secant y also becomes 1. So what is left? We get e to the power c equals 1. So the equation that is displayed in red simplifies to secant squared y plus secant y tan y equal to secant squared x plus secant x tan x. E to the power c is what? 1. And so you simply get secant squared y plus secant y tan y equal to secant squared x plus secant x tan x. This equation will force you that y equal to x, or does it? I think you should investigate that. So does it follow that the solution is given by y of x equal to x? So what happens to the equation? E to the power c we figured out is 1, and so this equation reads secant squared y plus secant y tan y is secant squared x plus secant x tan x. So from this, does it follow that y of x equal to x? I think you should definitely spend some moments and think about it. We go to the next problem. Solve the differential equation 1 plus e to the power t dy by dt plus e to the power t minus y equal to 0. Again, the question is, does the solution escape to infinity for some finite time? Solve the differential equation also. Does yt have a limit as t goes to minus infinity? So, number of questions. You are given a differential equation. It's a variable separable equation. You divide by e to the power minus y and you divide by 1 plus e to the power t. So, we do that. Abbreviating dy by dt by y prime, we get e to the power y prime plus e to the power t upon 1 plus e to the power t equal to 0. You can immediately integrate this with respect to t and you get e to the power y plus log of 1 plus e to the power t is c, where c is a constant of integration. The constant of integration must obviously be positive.
the term e to the power y in 1.12 is positive and log of 1 plus e to the power t is also positive. So the constant of integration must be positive.
Okay, so the differential equation also shows, so what does the differential equation tell you? It tells you that y prime is negative. From the equation, you immediately see that y prime is negative because exponential functions are positive. So from the equation, you see that y prime is everywhere negative. So y is a monotone decreasing function. Y is a monotone decreasing function. And suppose that the solution were to live on the whole interval 0 to infinity. Suppose there is no escape to infinity in finite amount of time. There are two possibilities, two scenarios. The solution escapes to infinity, there is a finite time catastrophe, or the solution lives forever. Suppose the solution lives forever, then what could you do? We could let t tend to infinity in 1.12. Let's go back to 1.12. So this is an equation, and if this were to be valid for all values of t, that is, the solution were to live forever, then I can allow the t to go to infinity. If t goes to infinity,
What happens to the log of 1 plus e to the power t term? Log of 1 plus e to the power t goes to infinity. The other term e to the power y is also positive, so the left hand side goes to infinity, whereas the right hand side is constant. How is this possible? We have a contradiction. It is not possible that the solution lives on the whole interval 0 infinity.
the solution cannot live forever. The solution must escape to infinity in finite amount of time. Well, will it go to infinity or will it go to minus infinity?
If y of t goes to plus infinity, then e to the power y would go to plus infinity, and 1.12 forbids this from happening. So in this case, y of t must go to minus infinity, and we should get e to the power y going to 0.
What is the largest interval 0t on which the solution is defined, and what happens as t goes to? That is, what is the time of existence? That is, there is a finite time in which the thing is going to escape to minus infinity, and that finite time is capital T. So what is the value of capital T? So little t goes to capital T. So in the equation 1.12, you will get log of 1 plus e to the power capital T. But as little t goes to capital T, y goes to minus infinity. The e to the power y term disappears, and you get, and the right hand side is a constant. And so you can calculate what the capital T is going to be. What is that capital T? It is going to be given by e to the power capital T equal to e to the power c minus 1. So what is capital T? It's going to be log of e to the power c minus 1. So that basically answers this first question for you. I leave the second part for you to think over. You should have some food for thought. We will now look at the special case. What happens when we look at this differential equation which is variable separable? Dy by dx equal to gx into hy. Remember, we have been all the time dividing by h. We also been using the fact that gx is not 0. Well, what is the problem with h vanishing? If h becomes 0, we can't divide by h. If h is not 0, we can still divide by h, but what about g being 0? What is the harm in g becoming 0? The harm is that, remember, we have been using the change of variables theorem, the substitution theorem. Remember, we have been using the substitution theorem many times, and we can only use the substitution theorem, the derivative is non-zero throughout the interval. Worry about what happens when this g of x is 0. Okay. Again, I say, usually in real life situations, when differential equations come to you, they'll come to you with prescribed initial conditions. And so the initial conditions are such that y of x naught equal to y naught, where x naught is some given time and y naught is the state of the system in time x equal to x naught. Now suppose if h of y naught happens to be 0. Suppose if h of y naught happens to be 0, then the right hand side is 0. Notice that the constant function satisfies the differential equation, right? When you differentiate a constant function, the left hand side is 0. And the constant function y equal to y naught, when you plug it in, you see that the right hand side is also 0. So 0 equal to 0. Yeah, so the constant function y of x equal to y naught satisfies the differential equation. It also satisfies the initial condition. Function is everywhere, the y is everywhere equal to y naught, and hence in particular at x naught also it's equal to y naught. So we have solved the initial value problem, namely the solution is the constant solution. So the case when h is 0 can be handled in this very trivial fashion. On the other hand, if h of y naught is not 0, then we can divide by hy. Remember, we are only looking at the situation around in a small interval around x naught. Remember that the solution may not live for the whole interval of time, and the entire drama is valid only in the neighborhood of the initial conditions. So x is close to x naught and y is going to be close to y naught. H of y naught is not 0, so h is not going to be 0 near y naught by continuity. So I can divide by h of y naught. But g of x naught could be 0, in which case our use of the change of variables formula, our use of the substitution theorem is suspect, in which case what we shall do is that we shall assume that g is 0 at say finitely many points. In between places where g is 0, g is going to be strictly positive or strictly negative, and we'll have to analyze the situation on the different intervals on which g is non-zero. It is g is 0 at isolated places. That has to be dealt with separately. Alright. As a next example, we take a very popular problem from geometry. This problem is there in a variety of different books. It's so popular that I really don't recall where I saw this example for the first time. So I apologize for not giving you a reference for this. Find a plane curve. What is the problem? Find the plane curve y equal to fx with the property that all its normals pass through the same point. Geometrically, your geometrical intuition should tell you that this curve must be a circle. Well, then let us back up this intuition with precise mathematical reasoning using calculus. Let us assume that the point through which all normals pass is the origin. And let us take a typical point x0, y0 on the curve with equation y equal to fx. So what is the slope of the normal at x0, y0? Well, there is really no need for me to draw a picture, because I urge you, as you listen to these lectures, I urge you to doodle and draw the pictures yourself. It is so simple that there is no need for a picture. You also have your sharp imagination. You got this point x0, y0 on the curve. At the point x0, y0, what is the slope of the tangent? F prime x0. So what is the slope of the normal? The normal is perpendicular to the tangent. So the slope of the tangent is f prime of x0. The slope of the normal is going to be minus 1 upon f prime of x0. That's what you see in the slide. Minus f prime of x0 to the power minus 1. So what is the equation of the normal? The equation of the normal is y minus y0 equals m into x minus x0. Y minus y0 equals m, the slope, into x minus x0. So a little rearrangement gives you y minus y0 into f prime of x0 plus x minus x0 equal to 0. This is the equation of the normal. Now what are we saying? We are saying that this normal passes through the origin. So the origin satisfies this equation. That's when I put x equal to 0 and y equal to 0, this equation should be valid. So let us put x equal to 0 here and y equal to 0 here. What do we get? We get the equation x0 plus y naught into f prime of x naught equal to 0. This is equation 1.13. So we see that 1.13 must hold at all the points on the curve. At all the points on the curve, this equation 1.13 must hold. So of course, the next thing to do would be to look at equation 1.13 and simply drop these annoying subscripts 0. So let's drop the annoying subscripts 0. So since this holds for all the points x0, y0 on the curve, and so we write 1.13 without the subscript 0 and using the familiar notation dy by dx in place of f prime of x. And so what does 1.13 go? X plus y dy by dx equal to 0. This
Y dy by dx equals minus x.
it's a variable separable differential equation. It is a variable separable differential equation, and you can immediately integrate it and you can get y squared by 2 equals minus x squared by 2 plus constant, or y squared plus x squared equals 2c. The curve is a circle. So our intuition has been backed up by precise mathematical reasoning using calculus. So the curve is the curve with the property that all normals pass through a point is a circle. So now the next item in our agenda is to study a very interesting example from Rainville's book Elementary Differential Equations. The exact reference will be given later at the end of the example. So what is the example? We take a variable separable equation, square root of 1 minus x squared dy by dx plus square root of 1 minus y squared equals 0, y of 0 equals root 3 by 2. Proceeding as usual, we get integral dy by root of 1 minus y squared plus integral dx upon square root of 1 minus x squared equal to 0.
The y integral, as everyone knows, is sine inverse of y, and the x integral is sine inverse of x. Integral of 0 is of course a constant.
Now to determine the constant of integration, we put in the initial data, the initial conditions. What are the initial conditions? When x is 0, what is y? Root 3 by 2. Root 3 by 2. So put x equal to 0 here and y equal to root 3 by 2. So sine inverse of root 3 by 2 is pi by 3. So value of the constant is pi by 3. So that's about it. I mean, it's a very easy problem as far as solving this differential equation with this initial condition is concerned. But we should not stop here. We should in fact take our investigation a little further and some very interesting things come up. So while this may sound pretty easy, let us see the solution in some detail. So what do we get? Value of the constant is pi by 3, remember? So we get sine inverse of y equals pi by 3 minus sine inverse of x. So let's take the sine of both sides. We get y equal to sine of pi by 3 minus sine inverse of x. Recalling the addition formula for sine. What is the addition formula for sine, please? It is sine of a plus b is sine a cos b plus cos a sine b, and sine of a minus b is sine a cos b minus cos a sine b. So this is going to be sine pi by 3 cos of sine inverse of x minus cos pi by 3 into sine of sine inverse of x. Alright, so that gives you y equal to root 3 by 2 cos of sine inverse of x minus half x. Then we should probably bring this half x on the left hand side and square. When we square, what do we get? Y plus x by 2 the whole square is 3 by 4 into cos squared sine inverse of x, and which is 1 minus sine squared sine inverse of x. What is 1 minus sine squared sine inverse of x? It is simply 1 minus x squared. It is simply 1 minus x squared. Well, the next thing to do would be to expand this and collect terms. Well, we get the more elegant formulation, x squared plus y squared plus xy equal to 3 by 4. Notice how different is this avatar of the solution from our previous avatar. Our previous avatar was sine inverse of y plus sine inverse of x equal to pi by 3. And this, now we got a very different looking equation. The solution y is implicitly given in terms of x. Let's proceed a little further. Let us not give up at this stage. Let us try to understand what this curve is. It's a curve in the xy plane. If the xy term were not there, had it just been x squared plus y squared equal to 3 by 4, we will be very happy and we will be drawing a circle of radius root 3 by 2. But unfortunately, this xy term is going to complicate things slightly. But we would like to understand what kind of curve is this equation represent. X squared plus y squared plus xy equals 3 by 4. To examine the nature of the curve x squared plus y squared plus xy equal to 3 by 4, let us put little y equal to 1 upon root 2 into capital X plus capital Y. Little x equal to 1 upon root 2 into capital X minus capital Y. For those of you who have learned the coordinate geometry properly, will recognize that we are rotating the coordinate system by angle pi by 4. We are rotating the coordinate system through an angle of pi by 4 and trying to understand what happens to the equation x squared plus y squared plus xy equal to 3 by 4. Well, the new equation, the equation of the curve in the new coordinate system is 3x squared plus y squared equal to 3 by 2. Lo and behold, this is an ellipse. 3x squared plus y squared equal to 3 by 2 is a standard ellipse. Now let us look at this ellipse a little carefully. The ellipse in the new coordinates is 3x squared plus y squared equal to 3 by 2. Let us try to figure out what is the semi-major axis and semi-minor axis of this ellipse. Let us divide the equation by 3 by 2 so as to make the right hand side 1. So if we do that, what happens? Let's divide by 3 by 2. What do we get? X squared upon half plus y squared upon 3 by 2 equals 1. So what is the semi-major axis? The semi-major axis is square root of 3 over 2. The semi-major axis is square root of 3 over 2 and the semi-minor axis is 1 upon root 2. So the standard ellipse, the major and minor axis are along the coordinate axis. But remember, what did we do? We rotated the coordinate system through angle pi by 4. We rotated the coordinate system through angle pi by 4. So what are the major and minor axis of the original ellipse? It is the line sloping at an angle of pi by 4 and the other line which is sloping at an angle of minus pi by 4. So so x squared plus y squared plus xy equals 3 by 4 is a standard ellipse rotated by angle pi by 4. So this beautiful example is from Earl D. Rainville's Elementary Differential Equations, the 5th edition. This book has undergone many editions. It has come to the 10th edition, but I am referring to the 5th edition and the page numbers refer to the 5th edition. So this problem appears on page 42-43 of this beautiful book, and it's remarkable collection of problems that I urge you to look at. The birth of the elliptic functions. Now you might think that this particular problem was pretty simple. It's a very simple problem. Integral dy by square root of 1 minus y squared plus integral of dx upon square root of 1 minus x squared equal to 0. You might wonder that why do we do such trivial exercise? Perhaps some of you might find this boring, but I want to convince you that this leads to something exceedingly non-trivial and very exciting part of mathematics. The idea is to replace this y squared by y to the power 4th and this x squared by x to the power 4. Now, if you have been working out lots of integrals in your integral calculus classes, you will know that dy by square root of 1 minus y to the power 4 cannot be integrated. You cannot compute the indefinite integral of dy by square root of 1 minus y to the power 4. Well, so what happens is that whatever we had done, we have got this equation sine inverse of x plus sine inverse of y equal to c in this elegant form, x squared plus y squared plus xy equal to 3/4. So somehow you should probably get the idea that the differential equation is somehow related to an ellipse, second degree curve. So Euler went further and he looked at this situation, integral 0 to u with a fourth power in the denominator. So whatever we have done, what we have just done can be slightly written in different form. It is the same idea, but slightly in a slightly different avatar. Integral 0 to u dt by root of 1 minus t squared plus integral 0 to v dt by square root of 1 minus t squared is again integral dt by square root of 1 minus t squared, but with the different limits, 0 to some complicated expression involving u and v. What is this complicated expression? It is phi of uv equal to u root 1 minus v squared plus v root 1 minus u squared. What Euler did was, he replaced the t squared by t to the power 4 and obtained a similar expression with a more complicated phi, and this was a very remarkable achievement because 3 decades later Gauss studied the inverse function. Remember, integral 0 to u dt by root of 1 minus t squared is sine inverse of u and its inverse is the sine function. Similarly, the function integral 0 to u dt by square root of 1 minus t to the power 4 also has an inverse called the elliptic sine function, and those were studied by Gauss 3 decades later, approximately in the year 1796, and Gauss obtained an addition formula for the elliptic sine function, exact an analog of the addition formula for the trigonometric sine function. So you see that what appeared to be a very innocuous looking differential equation has actually taken you through the gateway into a very magnificent part of mathematics, the theory of elliptic functions. A very beautiful description of these things can be found in A.I. Markusiewicz's book, The Remarkable Sine Functions, for which I have given you the reference in the slides. So the idea was to take this simple variable separable differential equation and take it as an excuse to give you a glimpse of a beautiful part of mathematics.